This video will focus around two components. One, continuing our ability to solve for pressure, volume, moles, or temperature of a gas using the ideal gas law, and then also using the ideal gas law as part of a stoichiometric calculation, which is one of the hardest problem types we'll have for this unit. In class, we've dealt with the three gas laws so far: Boyle's law, Charles' law, and Guy-Lussac's law. Once we're in class together, we'll work on math problems for this. But just to review quickly the relationships, for Boyle's law, as pressure increases, volume decreases. And I haven't shown you a mathematical expression yet for it, but that's the one on the screen here. Charles' law, as volume increases, temperature increases, and vice versa. And we had a mathematical relationship there. And then Guy-Lussac's law, it was pressure and temperature, and this was the mathematical relationship. Now, if you look at all three of these variables, they can all relate together, because in one you have pressure and volume, in one you have volume and temperature, and in one you have pressure and temperature, meaning all three variables relate to one another. If you relate all three together, you get something called a combined gas law. And what's nice about the combined gas law is you don't then have to memorize each of the three laws independently. They're all in this one equation. And if you're working with a Boyle's law problem, for example, where temperature is constant, you can basically drop out the variable temperature, and then you have the P1 V1 equals P2 V2. So the combined gas law sums up all the mathematical relationships that you encounter in the gas laws into one equation that you can use. In terms of memorizing these relationships, someone came up with this a long time ago, and I love it. If you put these three variables into a triangle, inside the triangle, it goes alphabetical counterclockwise. Okay, so if you go counterclockwise, PTV. Outside these triangles, if you put the letters of the names of the laws on each line clockwise, you know which two variables relate for each equation. So Boyle is PV, Charles is VT, Guy-Lussac's is PT. Okay, so it's counterclockwise out in here and clockwise out here. So it's two different directions, but you kind of get the idea. So that's one way you can memorize this equation. When we're dealing with combined gas law problems, what you're going to see is always a change in conditions. I'll give you an initial state and a final state, and there'll be a change. That's what we're going to work on in class, what those problems look like. For the rest of this video, we're going to deal with the ideal gas law. The difficulty becomes when we just want to assess a sample of gas. Okay, we know there's a relationship between pressure, volume, and temperature, but if I just have a sample of gas sitting there at a certain temperature and a certain pressure, the question is, what volume will it take up? And the one component we haven't looked at so far is the number of moles, and how the number of moles present affects the change. For the combined gas law, we don't have to worry about the number of moles really, because that's not a component we're looking at here. It's not one of the ones you can change to affect the other ones. The combined gas law just does pressure, temperature, and volume. Once we look at the number of moles related to, we get something called Avogadro's principle. And if you remember, we had Avogadro with 6.02 times 10 to the 23rd, and this was his actual research that got to 6.02 times 10 to the 23rd. Okay. The first thing he was finding out, and I've mentioned this before, is that when he had equal volumes of gases at a constant temperature and a constant pressure, he was always finding that those gases would take up the same volume. So it didn't matter if he had oxygen or carbon dioxide or hydrogen or nitrogen. As long as he kept the pressure and the temperature constant, the number of moles would tell him the volume. So that constant temperature and volume that then was established as a reference point when talking about Avogadro's principle was STP, right? A standard temperature and pressure. That standard temperature and pressure was 273 Kelvin, or 0 degrees Celsius, and then that 1 atm at sea level. Now, in reality, most classrooms you're working in won't be at these, but these are essentially our reference points, okay? And then also the reference volume that's generated. So at the same temperature and pressure, equal number of particles per volume, 1 mole was 22.4. Okay, that's where all of this came from. Now the difficulty becomes if we're not at standard temperature and pressure. So standard temperature and pressure, so 0 degrees Celsius and 1 atm, anything you have is going to take up a volume of 22.4. But if you vary the temperature or vary the volume, that number changes. So how do we calculate it? What we have is something called an ideal gas law. And an ideal gas law has a relationship between pressure, volume, and temperature that then allows you to calculate your number of moles. So this equation here gives you a relationship between volume and moles, given the fact that pressure and temperature are going to change. Okay, so PV equals nRT. Pressure, P, can be measured in ATM or kPa. Volume has to be measured in liters. Temperature is in kelvins. Your N is your number of moles. And then you see this random thing called an R. An R is just a constant. It's called the ideal gas law constant. If you rearrange the ideal gas law into more like the combined gas law format, you can see that PVT from the combined gas law is still here. We have an additional component of the number of moles and how that affects these, but essentially that is equaling a constant, that R. That R then just gets wrapped into the equation, and that's our constant that allows us to relate all these variables to one another. Generally speaking, this is the number that throws people for a loop. I don't know why. Okay? A constant is a constant is a constant. It's just a number that you will use for every single ideal gas law, and it's used in order to have your final values be correct. Okay? Without the R, your values would be off by a factor of 0.08206 if your pressure is measured in ATM, for example. So I'll always give you two constants on your test, one R that's measured in ATM, one R that's measured in kPa, but either time all the rest of them will be measured the same way. So this, for example, is one of your R's for when your pressure is measured in ATM. So this is your number, R. This is the number that you'll use as part of your calculation, 0.08206. This whole thing at the end here, okay, this whole thing is just your unit. It's confusing for people because they feel like they need to fill it in, like, oh, I got to put a volume and pressure, blah, blah. No, this is just your unit. It's there so that when you properly apply this mathematical calculation, the units will all cancel out and you'll get the unit you want. Okay? I'll show you how that works in our next calculation, but the biggest thing about your R is this is your numeric number that you plug into your calculator. This is a unit. You have to write it down, but it should not be taken into consideration for any kind of calculation. You don't plug a volume and a pressure and a mole number and a temperature into this unit. It is a unit. Just like for density, we have 0.113 grams per mil. You wouldn't all of a sudden plug a mass and a volume into this unit, right? It's the unit on this number. This is the unit on that number. It's a really big unit in that it has lots of variables in it, but it's just a constant. Okay? Don't worry about all of that junk. So let's see how this works mathematically. I have an example problem on the screen for you. If you have 0.250 grams of carbon dioxide in a certain container at a certain temperature, what's the pressure? So you can tell this isn't a changing situation. We don't have two pressures, two volumes, two temperatures, or anything like that. We just have a static situation and we're asking for one of our variables, which means we're going to use the ideal gas law. So when I problem solve these, I write down the variables in my ideal gas law, P, V, N, R, T, and I just start assigning their values. So pressure is what I'm looking for. And it wants it in ATM, so the R, if I look it up, is that 0.08206 that we need. That's a constant. And the unit on this then is liters ATM mole K. Because these units need to go away, these dictate the units I have for all the rest of these. So I give you a volume of 350.0 milliliter. But if I plug that into a calculation with this R, liters and milliliters will not cancel. This has to be liters so that it cancels with this liter. So I've got to get this into liter before I can stick it into my equation. Okay, so it's 0.3500 liters then. Temperature is given to me. It's given to me as 400 K, which is great because I have Kelvin as part of my unit. If this were in Celsius, I'd have to convert it. And now we have the problem with mole. I don't give you mole amounts. I give you that I have 0.2500 grams of CO2. But I don't want grams. N is mole. Can you get gram to mole? And you better be saying yes, because you see gram, you think mole, you think molar mass. Okay, gram to mole is a piece of cake. I'm going to go gram to mole of this using my molar mass of carbon dioxide, which is 44.009. 0.005681 mole. Now I have all of my units assigned. I only have one question mark, which is good because in the end you can't get more than one out of one equation. And now we're going to plug it in and solve. So the equation again is PV equals nRT. Pressure is my question mark. My volume is 0.3500 liters. That's going to equal my number of moles times my R times my temperature. So, to solve this in your calculator, you're solving for this P. So this times this divided by this will get you P. And now you can see how units cancel. If you take this unit times this unit, your moles will cancel because you have a mole on top and a mole on bottom. You take this times this, the K's will cancel because you have a K on top and a K on bottom. If you take this and divide it over to the other side, you'll have a liter on the bottom and a liter on the top. So they will cancel and you'll get your final answer in ATM, which is what you wanted. So that R unit is just there to drive your units through the problem so you end up with your final answer in the appropriate units. Okay, if you put this all in and plug it in correctly, you should get that you have a pressure equal to 5328 ATM. 4 sig figs, because every single number in the problem contained 4 significant figures. That's all I want you guys to deal with for tonight. We'll deal with the stoichiometry problems together in class tomorrow. They're by far your hardest problems. And all the stoichiometry problems do beyond what I just did is deal with that mole measurement. Okay, you can potentially calculate a mole amount from a stoichiometric calculation and then use the ideal gas law to determine pressure or volume or some other variable. Go ahead and do the form. Have a nice night.